Welcome to the pre-recording of lecture 13 of MCS 572. So this lecture is on tasking. Again, we introduced tasking in the last lecture, but then with OpenMP. So the purpose of today is to redo the previous lecture, but now with Julia, which is more higher level than C. And in this part of the course, this is already our 5th week, we are considering parallel shared memory computers. So in this lecture, I will very closely follow a blog post. So in some sense, this is all very new, but it works. Okay. When we introduced OpenMP, we were extending the C language with some directives. We have to compile with a special flag, and then we have to link with the OpenMP library. That is an extension of C. And there is silk, so in some sense also C will be or is already extended with multithreading and tasking. But here we are looking into programming system or a programming language that is equipped with tasking. So here is the blog post. I have not checked as of today whether this is still up. So the current version of Julia is 1.8. I have tested this, but I have not updated the slides. So everything is still working with the most recent version or the current version that I'm using of Julia. The bottom line of this slides is that tasks are lighter and more logical than threads. Threads are typically mapped to the processor cores. Tasks are typically functions or even individual instructions. So it's a lot faster to launch a task than it is to launch a thread. Also, termination of tasks are much faster than threads. And in the beginning of the course, in week 2 and 3, we considered message passing. There we actually considered processes. So the consequence of this is that the programs that we consider today are actually all going to be running very, very quickly. So the benefit of tasking is that your parallelism can be a lot finer. So this is a course on supercomputing, but also for this course, for this lecture here, you don't need your supercomputer. You can work everything you can do everything on your laptop. Okay, I follow the blog post, which is also very carefully, which is also very similar, I must say, to the OpenMP tutorial. So we start with the Fibonacci numbers. The Fibonacci numbers are just an academic example, and you should never compute the Fibonacci numbers recursively. But there are many divide and conquer parallel patterns that follow this sequence. And I will illustrate this with the recursive trapezoidal rule, like was done in the previous lecture. So it is a parallel pattern. Okay, it allows me to introduce the constructions that will be defined by the Julia programming system. So tasking, again, you will launch some threads. So perhaps you want to say, look, I want to use 4 or 8 threads, and then it's the responsibility of the system to map the tasks onto the threads. So typically, I should have said this earlier, so if one thinks multi-threading, then one typically will not use more threads than the available processor cores. The number of tasks that is generated is typically does not correspond to that limitation. Okay, what are now the two basic constructs in Julia? We can spawn a task. So we start the task by this acrawl spawn, and then typically this is followed by a function. And recursion is possible here, as with the Fibonacci numbers. Then there is the synchronization that is in Julia implemented by the fetch. Fetch waits and then returns the value that was computed by the function that was started by the task by the spawn. Okay, so so this is something that probably I may have explained already, but to keep these lectures self-contained, it's useful if we want to pass input, so this is interactive parallel programming. If we want to time, then that we don't have the additional delay of the slowness of the user typing. So with Julia, we can get the input from the command line. I must say that we started in this course high-level parallel programming from within a JupyTer notebook. We are still actually here. We actually have kind of. I'm still very much running this course now with at the terminal prompt, at the command prompt. Although it should be possible from within a JupyTer notebook. Okay, so we can determine. We could determine. So before the program launches, we determine how many threads that the program should use. So this is multi-threading. So we say that 8 threads here will be used, and the program will confirm the number of threads. So we had the work crew model that was implemented in Julia. So that is multi-threading, where you as a programmer are going to map what every thread does explicitly. So this is a more coarser and a more restricted model of programming. Here we could rewrite our application that whatever the recursion does, every recursion can be rewritten as if you use a stack. We can rewrite the recursion using the stack explicitly and then see the contents of the stack as the jobs that need to be done. That would be tedious for us programmers to do. Instead, we work with this spawn and the fetch. So the program is short and self-contained. It fits on one slide. So here explicitly imported the acrawl spawn, and I did not have to do that with the fetch. Perhaps the first statement might not be strictly necessary. Okay, this is it. This will compute the 10 Fibonacci numbers by running the multi-threaded version with 8 threads. And I didn't draw the tree of recursive calls, but this tree tends to grow exponentially. So you may have close to the order of 2 to the power 10 tasks that are being run. So it's mainly important that this is not going to lead to parallelism, but there is no problem of launching thousands of tasks. There would be a problem launching thousands of threads. Okay, this slide explains, summarizes what the program does. You can also time it with the time. The time will give you the wall clock time. In this construction here, this is the most informative measure. So in the next lecture, I will say something more about performance evaluation. So there is the creating and there is the synchronization. Very similar to what we have seen with parallel regions in, when we started OpenMP with the multi-threading. But here it can happen without essentially changing the logic of the program. So that is important. Okay, Fibonacci numbers are a parallel pattern, and that pattern is applied here with recursive quadrature. So we want to approximate an integral of here one function f over the interval ab. So the function f is typically a very expensive function to evaluate. So the cost is in the number of function evaluations. And now here, the parts can be computed independently from each other. So in some sense, with the Fibonacci numbers, there was only the function calls. There was actually no computation happening inside the call, and the computation that happened was the plus. Here actually the tasks will independently run many function evaluations. And the function evaluations are constructed, are divided in this divide and conquer manner. This may have a numerical benefit, as I alluded earlier, so perhaps I should have had the 3 is somewhere here, but before I forget, let me say it, that if you have to make very long sums, say millions and billions of numbers, then doing the summation in a parallel recursion can be shown to be numerically more advantageous. So if you have a million sums to do, 2 to the power 20, then every number will only be involved in 20 additions. And that's kind of the intuitive argument, so that the summation happens numerically in a more stable manner, so less round off. So this is not a numerical analysis course, but there is a benefit of also running it this way. Here we are interested in correctness, so the correctness and seeing if there is actually now really a speed up. So that's essentially the goal of this example here. So I take a very simple function for which the integral over the interval 0, 1 is the transcendental constant e minus 1. Then this is a divide and conquer recursion where the level L here is the controlling parameter. So I have to provide not only the number of function evaluations, the bounds of the interval, but also the depth of the interval. So I'm at the leaves of the tree if the level equals the depth d. Okay, and that's essentially it. So we did parallel numerical integration before, but then with OpenMP I had to define explicitly that these A, B, and the C bounds were private, so that every thread would have its own copy. So the advantage of having the tasking be done in this way is that I do not need to be concerned about where these variables are. Okay, so here is the tree of function calls. So what happens at the leaves? So the leaves actually are now where all the computations are happening. So here there will be as many tasks spawned as there are nodes in this tree. At the nodes, there is only one addition that happens, and the addition happens towards the root of the tree. So when the recursion terminates at the root, there will be only the root left, and that will have the result of the integration. Okay, so at every level, if we are not yet at the depth of the recursion, we will spawn a task, and there will be the synchronization. So you see exactly the pattern of the Fibonacci rule, except for the Fibonacci rule, we are now calling the recursive trapezoidal rule in the general case, and at the leaves, when the level equals depth, then we are applying the trapezoidal rule. So it looks a little bit more complicated because of all the arguments, and there are still things that can go wrong, in particular the distinction between the calling the recursive rule and the trapezoidal rule. So, but the logic should be quite clear here. Also, there in the number of threads, the number of tasks that is spawned equals the number of nodes in this tree. So it is a very clean logic. I don't need to worry about where the variables are. So you see there is a new middle. So the middle was called the C in the previous slide. So in the middle of the interval, that will be shared between the two threads. But in functions in Julia, there are functions properly. If we want functions that change the argument, we have to let the name of the function, we have to append the exclamation point of it. But because these arguments are essentially values, there's not that much that we need to be concerned about. Okay, also the level, actually. The level is a parameter in the function, but then you see the level plus 1. So with each spawning of a task, the level actually is updated. The depth and the function, they are essentially constants. Also the n, so they could eventually be moved to global parameters. But for all purposes, this function nicely fits on one slide, and it defines both the logic and the parallelism. It's very clean. So I did not update my slides for this lecture. You're more than welcome to experiment with this on the current version of Julia 1.8. I run this with the command line arguments. So 4 is the number of subdivisions that I make. The number of threads is increasing each time. So I go from 2, 4, 8. And you see that the first time, the real, is the wall clock time. From 2 to 4 threads, it drops from 5.2 seconds to 3.1 seconds. And then with 8 threads, it drops down to 1.9 wall clock time, a little bit less than 2 wall clock time. So I say that there are 4 depths. So that means that there are 16 leaves. So there is work for 8 threads, and the slide was probably too small for this, but you see that the 8 threads actually, they gave rise to a good speed up. not optimal, but the level is also quite fine. So this is a computation that takes seconds. Each time I give the error, so the result is each time the same. So this is a show of correctness. You see the system time remains very small. So with message passing, there's a communication overhead. Also with multi-processing, there would be a lot more system time. Also with pure multi-threading, perhaps you may have that. You see the user time is the user CPU time. And that increases. So that means that there are many more threads being active. So it would be wrong to report the user time in examining the performance of this function. So it is not optimal. And I'm not saying that this is the best way to do it, but we have although perhaps the numerical stability in mind, and it may be better for certain type of integrals, especially if one is to sum numbers of different magnitudes. There it might actually matter. Okay, so this is the essence actually of the lecture. I'm halfway. I will show more examples. Here is mergesort. Mergesort is an n log n sorting method. And if the number of numbers that you want to sort, or the number of items you want to sort, is of the order 1 million, then it definitely pays off to use an algorithm such as this, an algorithm that is not quadratic in the size of the sequence to sort, but that is n log n, quasi-linear, as they also say. Here is the algorithm. Let me go through it. The base case is when there is only one or no elements. It is a divide and conquer method. We will split the sequence into equal halves. The recursive sort will be applied on the first half and the second half. Here you see again the same pattern as Fibonacci, but the sorting takes time, and also there is the work. What will be done is the merging. In order to make real progress, the sorting, it could be defined by functions, so that each time you return, when you split in equal halves, you return two new sequences, and but that will be very terrible for the memory. I mentioned functions that modify arguments. We will see them here with this exclamation point. And here I'm following also this blog post. So if you have never seen mergesort, then the advantage of this construction is that you can stay close to the logic. Here it is. The function parallel sort. So we have the sequence v. So the exclamation point says that we are going to change v. So we will sort. Actually, we will only apply the recursion when the number of elements is larger than 100,000. So there is the base case. So when there is only one element, so low and high are the lower bounds and the higher bounds, the beginning and the end index of the array that is being sorted. So we start by default at 1, and the high is by default the length. It makes it very easy to call the sort. Sort, Julia has a built-in sort, and that will be called if the length of the list is less than 100,000. So these are the two base cases. There is a return here. There's actually an explicit return that's being done. So, what happens is that we will find the midpoint. And this is here with this fancy division. We will sort the first and the first half with the first task, and the second task will do the second half. So this is the recursive psort on sequences longer than 100,000, and that will immediately then spawn the other programs. And then comes the merge, and that's where the actual work is. And here I was kind of discouraged. I didn't put it on the slides. So I can go to this, and I will do so in the actual lecture. But the programs are posted. So in there, I think the code also got kind of messy. But the work happens in the merge. So here I generate... So there is the compilation overhead. So there is the time that comes from the psort. So there is the built-in time in the Julia system that has a very refined timer. It will also list the percentage of the compilation time with each run. Okay, for correctness, I copy. So we have sequence B that gets sorted. The fact that it is a copy allows to test for correctness that we haven't lost any numbers. Okay, so here is the construction for 1, 2, 4, 8 is the number of threads. I did it in the previous runs with each time at the command line, so there is a more efficient way to do this. So you can actually add the prompt, do this shell construction. So there are the runs, and you see that what is reported by time decreases gradually. We can also compare the wall clock time. So with 8 threads, we have 1.2 in the wall clock time. But what Julia reports is 0.6 seconds. So the wall clock time lists everything. That's also, then you should in essence have this this first timer, this first compilation stage out. So there's actually no compilation done anymore with the time that is reported by Julia. Okay, so that is a recursive sort. You see that, and I'm actually giving a little bit of preview on the next lecture. Look at the number of allocations, and there is also the GC, the garbage collection time. So this is a memory bound computation. So this is where the memory transfers are actually quite substantial. Sorting is such a... the other computation was the numerical quadrature. And here in our case, it was the simple exponential function. But if you have a complicated function to integrate, then it also starts to become compute bound. Okay, so I will conclude with the multi-threaded matrix multiplication. So in the OpenMP lecture, the blocked matrix multiplication was defined. at a very high level with the in and out dependencies. Now, of course, Julia is a language geared towards scientific computing, and there the linear algebra module is immediately been built in. So as a Julia programmer, you would use the built-in matrix multiplication. Here is the test. So just to test how the constructions work, space is allocated for the result C. So what the mul exclamation point does, it multiplies the matrices A with B and it assigns it to C. So you can see from the two very simple matrices A and B that the result is indeed the product that is stored in C. Okay, so this is called the inplace matrix multiplication. The user is responsible for allocating memory. So here I did the matrices were both square. So otherwise you will need to use the zeros construction to make a matrix that is of the proper dimensions. Okay, you can specify the number of threads that the basic linear algebra subprograms should use. And here there is actually no compilation that will happen. Everything will be done in highly tuned and highly optimized compiled software. So we can set the number of threads, and we do this at the command line. So this will get the number of threads in the P and also get the number of dimensions, and we will time it. So we did something like this before, but this is good to transition to the next stage, the scalability investigations and the performance evaluations. Here I picked 8,000 as an exercise in preparation for the next lecture. Find the motivation for the 8,000. So there is somewhere a sweet spot. If you go less than 8,000, you actually will not observe speed up. So that's actually the point here. You go from 20 seconds to under 2 seconds using 32 threads. And I should say that this machine had 44 cores. So I was not even at the fullest capacity. But you see that this is also very memory intensive operation. So there are 2.7 million allocations, and it uses 130 megabytes of storage. But we have a very nice progression of the running times. So just by using the built-in constructions. Okay, to conclude, so you can test the peak performance by using the double precision. So this is one of the routines, the Gaussian elimination. And you see here the 8,000 comes here again. The 16,000 might actually be better. We have more. The peak flops actually is increasing. With 4,000 it goes down. And I picked 8,000 and 16,000, 4,000 because they are round numbers. It might actually be better to take powers of 2. That might be more beneficial. Okay, so 2 exercises at least. I have not listed them. So in the next lecture, I will address performance models. So thus far, we have times mainly. So here we do have the flops, the number of floating point operations per second that are being done. So the 10 to the power 11, so we have 10 to the power 6 million, 10 to the power 9 a billion. So this is 300 billion here if you have 10 to the power 11. So these numbers are looking actually quite good as far as performance goes. Okay, I had intended to speak about 40 minutes, but it went faster. So there are no online demonstrations. I wasn't prepared for this, but I hope in some sense the fact that it is shorter than the previous lecture is also kind of an indication that with the higher level of the Julia programming system, there is less to worry about, less to care about than with the OpenMP model that is on top of a C language that extends C. Okay, I hope that this was interesting.